Welcome my dear students, new session. In the last class we discussed about the 1 onto linear transformation. We prove two results. One result is we have to show that if the dimensions of both the vector space are the same dimension vector space V and W, then if T is 1 then T is also onto. Also we show that if V and V2 V are the basis for a V, then T of V1, T of V2 Vn are the if T is 1 and onto linear transformation, if V1, V2, Vn be a basis of a vector space V and T linear transformation is a bijective 1 and onto, then the T of V1, T of V2, T of Vn are the basis of a vector space W. In this class we discuss about the inverse of a linear transformation. Because in the last class we have the linear transformation that are both 1 and onto play an important role. We give them a special name with the following definition is a non-singular, or we can say that as sometimes also is called as a isomorphism. So a linear map T from U to V is said to be U and V are the we have a two vector spaces is said to be non-singular if it is 1 and onto, or such a map is also called as a isomorphism. Clearly we can say that if we have a T from U to V is 1 and onto, so we have a 1 and onto map. So this means is clearly called as a both 1 and onto, then we can say that this is, so this means we can say that clearly and that any function has an inverse, it is also is a 1 and onto. So you know that by the function, if we have a function from A to B which is 1 and onto function, then we can say that we can define a function from B to A f inverse is called as f inverse. So this means this is the function is we call f inverse B to A, and this called the inverse. If this is function is a 1 and onto, this inverse function is also is a 1 and onto. So this way we can just say that into this form we have a this is you have a, suppose we have a V and W vector spaces. So we have to like this, we have a V, this is mapped into the T of V, then we have to just say that T of V that means W can be, this map is defined from, this is a T from V to W, then we have a T inverse is always defined from W to V, and that is called as the inverse map is there. So a linear transformation is a non-singular if and only if it is an inverse. So by this fact we can say that any function has an inverse if and only if it is 1 and onto. So this means we can clearly say that if non-singular means if a linear transformation is 1 and onto, and if it is a non-linearly transformed, then its inverse is exist and it has an inverse. And then how do we have to find the inverse? So inverse linear transformation is nothing but we have a T from V to W be a bijective linear transformation. The inverse of this is equal to is the form of a T inverse is W, and then V is nothing but is equal to you have a T of W if and only if T of V is equal to W. So we have to define how we define this. We have to take any V belongs to the V, and so this means T of V you have a, if you have W, then you can say that V is nothing but is equal to T inverse of a W. You have to just say, so T V is equal to T inverse W if and only if T of V is equal to W. So if we have to define inverse of a linear transform in this form, but inverse is only applicable when this transformation T from V to W be a bijective, or we can say that is a 1 and onto linear transformation. Okay, let's try with the if T has an inverse transformation, so we refer as a T being as a invertible. To be invertible, T must be a both 1 and onto. This means that if a given linear transformation is bijective, then it has an inverse transformation. So by this definition we can say that if we have any linear transformation is given, if such a linear transformation is bijective, means is a 1 and onto, then its inverse is also exists, and that inverse transformation is nothing but is equal to T inverse is what from W to V, and this is defined in the form of this T of V is equal to W, then W is equal to you have a T inverse of a V. We have to define to this one. Okay, we try to from this identity transformation is an isomorphism, also called as isomorphism or is a non-singular. So I of v, you know that is equal to v is equal to always is equal to v. So this means you have to just say that I v inverse is also from v to v, and then you can just say that I of v inverse is the same as I of v, and it means inverse transformation, identity transformation of inverse of a itself. Why is in inverse of itself? This because of this. So you can say that I of v of v is equal to v, then by the definition we can say that I of v inverse of v is again v. So this means we can say that both the cases there. So I of v is the same as you have a I of v inverse. So means inverse transformation is a clearly. So isomorphism, I of v is equal to 0, v is equal to 0, the kernel of I v is equal to 0, so I is injective. Okay, we just the inverse transformation show by the is an isomorphism, means is a 1 1 and onto. Clearly this identity transformation is clearly 1 1 and also onto, because we have a both the dimensions of a same, we can say that, and also w belongs to I, w is also w. So every element of a v is an image. So this means this is clearly I of v is injective and surjective, or we can say that 1 1 and onto. So this means we say that identity transformation is always as an is a non-singular transformation, and this is called is also is a isomorphism. And inverse of a, this is I already explained you, the inverse of a this transformation is clearly is a itself. So I inverse v is the same as I inverse. So identity transformation is a non-singular transformation, and its inverse is itself. Now we try to find is this is a non-singular or not. First, then only we can try about the inverse. So first we check is this is a non-singular, means we have to find the kernel of a T, because these two maps are the same. So by use the theorem we have a, if dimension of a v is the same as the dimension of a w, and if T is we have a 1 1 if and only if T is onto. So we try to find the kernel of a T, that v is the element of a v such that you have a T of v is equal to 0. So this implies that you have a T of v1 v2 is equal to 0 0 r2, then you have a this is equal to v2 comma v1 is equal to you have a 0 0. This implies that v2 is equal to 0 and v1 is equal to 0. So kernel of a T is equal to you have a 0 subspace, and then this implies that you have a T is clearly this is a T is clearly you have a 1 to 1 linear transformation, and also onto T is onto. Why T is onto? Because by this result both the dimensions are the this vector space are the same. So this means T is clearly also onto. So T is 1 1 and onto, that means this means we can say that inverse is also exists, and we can say that T of inverse can be written in the form of, suppose we can just say that T inverse you have a, we can find as a element of a, you have a w1 and w2 is equal to you have a some v1 and v2. So this can be written as a T of v1 v2 is equal to you have a w1 w2, and then v1 v2 we have to define as a v2 v1 is equal to you have a w1 w2. So w1 is equal to you have a v2, w2 is equal to you have a w1 is equal to v2, w2 is equal to you have a v1. So this means we can say that T inverse you have a w1 w2 is equal to w1 w2 is equal to, so you have a v1 is equal to you have a w2 and w1, then T inverse is exists, and T inverse is the value of a T of w1 w2 is the same as the w1 w2 and w1 is there. So that means we can just say that into this form. So we have a inverse in give that the T is 1 1, and then also because every w1 w2 belongs to R2, there exists v, so T of v is w1 w2. So therefore v2 w1 is w4, and then we can say that is this RT is nothing but is equal to OR. So this means we can say that clearly T is also onto, and if T is onto, then T inverse is v2 into v1, then we can clearly we have to prove into this one. Now one more example, let T v be a this theorem, we have a T from v to v be a non-singular linear transformation. then T inverse W2V is also is a linear transformation and also non-singular, means 1 1 and onto. Okay, let's we try to first prove that T inverse is a linear. If we prove that T is then W1 W2 is the element of a W, and inverse means we have by the definition we can say that T of inverse is W1 is equal to some V1, T of inverse W2 is equal to sum of a V2, and T is you have a giving is a non-singular, means linear transformation, the T is 1 1 and onto. So this means V1 and V2 exist uniquely. So this means if we cause 1 1 and onto, that means we can say that this is exist uniquely. So this is clearly T is 1 1 and so V1 and V2 is uniquely exist. So T W is equal to T of V1 and W2 is equal to T of E2. Now we have to calculate W1 plus W2 is equal to T of V1 plus T of V2, because T is giving you a linear. So V1 plus V2, and then this implies that you have a T inverse of, by the definition, W2 is equal to V1 plus V2, and V1 is equal to, you know, a T of W1 plus T inverse you have a W2. So this means clearly we can say that T inverse W1 plus W2 is equal to T inverse W1 plus T inverse W2. So additive condition is satisfied. Now alpha is any R, so we have to just say that T of inverse we have a alpha times of a W1, and this is equal to some V, whatever this we have to just assuming this, and then we try to show that this is the form of a so this means W1 is the form of a this. So we show that this is equal to alpha times of a T inverse of a W1. Next we have to show this one. So this is clearly this. So alpha 1 W1 is equal to T of alpha times T of V, and because T is a linear, this can be written in the form of a T times of a alpha of V1, and now we take a alpha inverse T of this is equal to alpha of V1 and then is equal to this. So this is clearly we can show that this T inverse is a linear map. So if T inverse is a linear map, then we have to prove that the first part of this theorem say that is a linear. Now we show that T is non-singular, then T inverse is also is a non-singular. So we just show that prove that T inverse is a 1 1. So W1 is W2 is the element of a W. So T inverse W1 is equal to T inverse W2. We assuming that is equal to some vectors is equal to V. So this implies that we can say that T of V is equal to you have a W1 and T of V is also you have a W2. So this implies that we can say that W1 is equal to W2. So if T inverse W1 W2 is the same as this, then W1 is also equal to W2. So in this case we can say that T inverse is clearly is a 1 1. So we have to, by the uniqueness, image of T is a unique, so this means they must be are the same. So we can say that clearly T is 1 1. Now we have to try to show that this T is clearly is also an onto. So if we have a T inverse implies this, so we just try to for any element V belongs to, there exists an element W, T of V is equal to you have a W, and now therefore V is nothing but is equal to T inverse W, and clearly this is a by the definition of an inverse linear transformation. So we say that if we have a clearly if we have a T from V to W is a non-singular linear transformation, then T inverse from V to V is also linear and non-singular. So this means if we have a T is a non-singular linear transformation, then T inverse also is a non-singular linear transformation. Okay, so this means we can say clearly we say that if we have a this is the remark, we can say that if we have a linear transformation T from V to W has an inverse, if it satisfies these two conditions, T is 1 1 and onto. If first we check is T is a non-singular, if T is a non-singular, then we can say that the inverse exists. The next objective is we have to find the what is the inverse of this linear transformation. So that means if we have any linear transformation is giving, first we verify if the inverse is exists or not. First we check, is this linear transformation is a non-singular. If this transformation is a non-singular, then only we can say that is inverse is exists, and then we have to find what is the inverse of this linear transformation. If this set this linear transformation is not a non-singular, then we cannot say that. They clearly say that the inverse of a such transformation does not exist, and then we cannot find the inverse of it. Okay, so we just try to from this example. This example we take a P3 to R4. Now we have a polynomials of a degree 3, and then this clearly this is a linear. We can just take any two polynomials. If we have to take a Px plus Gx, Px is the form of this and Qx is the form, then the sum is, if we take a sum of these two polynomials, this can be written in the form of a naught plus b naught plus a1 plus b1 x plus a2 plus b2 x square. If operating t of this, so t of Px plus Qx by the definition is nothing but is equal to a naught plus b naught comma a1 plus b1 comma we have a a2 plus b2 a3 plus b3, and this can be written as a naught a1 a2 a3 plus b naught b1 b2 b3, and this is nothing but is equal to, you have a t of Px plus t of Qx and the satisfy. Similarly, we can show that t of alpha Px is equal to alpha times of a t of a Px. So this transformation is clearly is a linear. And now next we show that is a non-singular or not. So what just we check is the it is a 1 1 or not. So we take find the kernel. So kernel of this t implies that you have a t of this is a naught plus a1 x plus a2 x square plus a3 x cube is equal to 0 0 0, and this implies that t is defined in the form of a naught, and then we have a clearly a1 a2 a3 0 0 0 0. This implies that a naught is equal to a1 is equal to a2 is equal to a3 is equal to 0. So this means kernel of a t is nothing but is equal to, you have a 0 subspace, and this implies that t is clearly is a 1 1. And now if we have a naught a1 a2 a3, any element of the R4, this is imply a naught plus a1 x plus a2 x square plus a3 x cube is the element of a P3R. So this means we can say that this is clearly every element of a0 a1 a2 a belongs to there as the image of there into this. So this is clearly is also is a onto. So this means we have this is the element of a P2 this is P3R, such that you can just this is so we just say that into this form is equal to P3. Okay, P3 this is R4, sorry, is R4, and this is equal to, you have a P3 such that this is the element of this. We can say that clearly t of this is equal to this. So this means we can say that this is, you have a R4, this is, you have a P3. So clearly we can say that into this form we have to this is a we have a P, this is the image RT, and RT is equal to, you have a all of R3, then T is onto, hence T is a non-singular. So it is inverse is exists. If inverse is exists means T inverse of clearly T inverse of, you have a we can just say that is equal to a naught a1 a2 a3 is the same as a naught plus a1 x a2 x square a3 x cube. So this means T inverse in the form of this form and defined in the form of a is this thing. Now this is the very important result. We have to take any vector space to the R3 is a vector space. So in general we can just define such a map is also called as a natural isomorphism between Pn minus 1 to R to the power n. You see previously that we have to define is a P3 to R to the power 4. So this means clearly if n is equal to 2, so n is equal to, you have a 4 in this form. So in general we can define such a map from T from P of n minus 1 R to Rn by this form, then clearly we can say that is this clearly we have to prove above is clearly this is a linear and also 1 1, because if this kernel of this is equal to 0 means whole thing is equal to 0 or also onto, and then inverse of a such is equal to you have a defined into t of a naught a1 up to a n minus 1 is the similar we have to just say that in up to a n minus 1 is the form of a naught a1 x up to a n minus 1 x to the power n minus 1. So, this is naturally we can define into this form. So, clearly kernel of this p and then a n is equal to 0. So, we have to is all 0. So, this means kernel is 0. So, clearly t is a 1 1, and then since image of dimension of this and dimension of this are the same. So, t is onto because of by the result when dimension of v and w are the same, if t is 1 1 then t is also onto. So, hence t is a non-singular and then t inverse exists, and then t inverse exists means for any v belongs to the r to the power n, yeah, this is bold v. Okay. So, this is mapped to this is not t inverse maps to you have a p n minus 1 is t of this up to this, and this is called the natural isomorphism between these vector spaces. So, in general we can say that if we have any linear transformation from t from p n minus 1 to r to the power n is a isomorphism, and this is the inverse is also exists. So, this means clearly is a called is a natural isomorphism. Similar fashion we can define a natural isomorphism for a in general we can say that not for a p n to Rn we can just define any vector space V for a dimension n, and B is a basis of B an ordered basis of a vector space V. Then we define for any u belongs to the V there exists a unique scalar, so that u can be written in the form of a linear combination of the element of the basis. If we define a coordinate map t from V to R such that t of V is a coordinate vector, you know that the coordinate vector is what? This is nothing but is equal to, we can write is the alpha naught alpha 1 alpha 2 are the these scalars are the called is the coordinates vectors of this. We take if we write in the matrix form we write as a one is the column of this alpha 1 up to alpha 2 up to alpha n, and similarly for corresponding second we have a second column and so on. So, thus t of u we have defined into the form of a coordinate vector. The previous example we have to just you said we have to take a p2 n minus 1 to r to the power n. We have to define is the basis to we have a coordinate vector a naught up to a n minus 1. These are the coordinate vector. So, that means in general we can define a map. We have a V is a ordered basis, and we define a map from vector space V to r to the power n, and r to the how much defined is this is the element of r to the power n the coordinates vectors coordinates of the this linear basis element. So, corresponding to this ordered basis we have this coordinate vectors are there. So, the t of u defined into a this coordinate vector. So, this is clearly we can show that this is clearly is a linearity. Why t is an isomorphism? But first is linearity. Why is linear? Because t of u plus w is equal to this, and this satisfies clearly both the condition, because we have a alpha 1 alpha 2 take a 2 vectors. So, we have t of u plus v. So, we have a corresponding to u plus v alpha 1 plus alpha beta 1 and so on. So, this is clearly satisfied. You can just take a you have a t of u is equal to you have a alpha 1 up to alpha n, t of v is equal to you have a beta 1 up to beta n, then you have a t of u plus t of v is equal to you have a alpha 1 plus beta 1 and so on alpha n plus beta n, and then we take a u and v are the basis. So, u plus v is the element corresponding we write is equal to alpha 1 v 1 plus so on alpha n v n plus beta 1 v 1 up to beta n v n, then we have to write alpha 1 plus beta 1 v 1 and so on, and this is nothing but is equal to again the same. So, this means this is a linear and also also is a satisfy this condition. So, this means this map is defined from t for a coordinates. So, this is a vector is clearly this is a linear map, and also this is a 1 1 injective, why t of u is equal to 0, then all the coordinates alpha is equal to 0. So, u is equal to 0. So, clearly this means u is equal to 0 means is equal to, we can say that kernel of a t is equal to 0. So, means u is equal to 0. If u belongs to the, we can say u is belongs to the kernel of a t, and then t of, by the definition, t of u is equal to 0. This implies that u is equal to 0. So, this is kernel of a t is equal to, we can say that kernel of a t is equal to 0 subspace, and if the kernel of a t is 0 subspace, then we can say that clearly this is a 1 1, and we have to show that we have a 1 1, then we also show that is a surjective. Why? Because for any beta 1 Rn, u can be written in the form of a linear combination of a, this is the element of a v, and then t of u is nothing but is equal to, you have a by the definition beta 1 beta 2 beta n. So, t is 1 to 1 and on to linear transformation, that isomorphism between v to Rn. So, that means we generally we define this is any vector space to R to the power n in the form of a t of u is the scalars alpha naught up to alpha n, and this map is always as a non-singular map, and also is inverse is also exist in this form. So, in this form we have to take any vector space. In the previous example, in place of a v, we take a polynomials. Suppose we take a 2 by 2 matrices are here, then natural isomers between R to the power 4. I take a b, c, d and define the coordinate vectors of a, b, c, because this a, b, c, d corresponding to the standard basis of this can be written in the form f of 1 0 0 plus b of 0 1 0 plus c of 0 0 1 0 plus d of, you have a 0 0 0 1, and then this can be written as a b, c, d can be written as in this form, and then t of this is nothing but the coordinate vectors of this. So, these are the standard basis, ordered basis is there, and then by the previous we can just say that R2 is a special case of isomorphism map Rn m by n matrix into the coordinate vectors. So, this is also is a natural or called is a natural isomorphism between the m cross n to R to the power mn. So, in this way we can say that if we have a any vector space, this previous theorem result is saying that if we have a t from v to any coordinate vector map defined is always is an isomorphism, and such an isomorphism we have to call as a natural isomorphism. Okay, so now we have to just try to solve one more example, and then we have to conclude this session with this example. Determine whether the linear map defined by this t of x1 x2 alpha 1 x1 alpha 2 x2, where alpha 1 alpha 2 both are non-zero, is a non-singular, and then because it clearly is if a non-singular, then find its inverse. Because the dimension of both the vector spaces are the same, so is enough to for showing that the non-singular means we have a 1 1 and on 2. It is enough to show that t is 1 1, and by because the dimension are the same, then we can say that these two t is also on 2. If it is in non-singular, if it is non-singular, then we have to find the inverse also. Okay, so we have to try to first this, we have to find the kernel of this t. So, kernel of this t is equal to, you have a clearly you have a x1, x2 belongs to the R2 such that t of x1 x2 is equal to 0 0, and then we have a clearly by the definition we have a t of x1 x2 is equal to 0 0 0, implies that you have a alpha 1 x1 alpha 2 x2 is equal to 0 0, and this clearly alpha 1 x1 is equal to 0 and alpha 2 x2 is equal to 0, and then you have a given clearly giving the alpha 1 is not equal to 0, alpha 2 also not equal to 0. This implies that x1 is equal to 0 and we have a x2 is also equal to 0. So, we have x1 and x2 both are 0. So, this means we can say clearly say that this means kernel of a t is equal to, you have a 0 subspace. This implies that t is 1 1, and if t is 1 1, then by the because the theorem we can say that also t is also, you can say that t is on 2. Now, we try to find out what is the inverse. So, this means we can say that inverse of this, we can say that t of inverse, we can say that suppose x1 x2 is equal to some y1 y2. So, t of y1 y2 by the definition is equal to x1 x2, and then t of y1 y2 is defined in the form of alpha 1. You have a surface y1, alpha 2 y2, n is equal to x1 and x2. Now we have to find the alpha 1, y1 is equal to x1, alpha 2 y2 is equal to x2. Then because alpha 1 and alpha 2 are not equal to 0, so y1 is equal to 1 by alpha 1 x1, y2 is equal to 1 by alpha 2 x2. So this means T inverse you have a x1 x2 is the same as a 1 by alpha 1 x1, 1 by alpha 2, okay, 1 by alpha 2 x2. So this means we can say clearly this map is non-singular and is also is a satisfy. This is the inverse of a this linear map T from x1 x2 alpha 1 x1 alpha 2 x2 is the same as T inverse of x1 x2 is the same of 1 upon alpha 1 x1 into 1 upon alpha 2 x2. So this complete this solution of this problem. At this point I have to stop this class here. In the next class we continue some more examples of this non-singular and inverse linear transformations, how to find some other exercises. We try to find the inverse of a linear transformation. If it is a non-singular, then we have to try to find the inverse, how to find the inverse of this linear transformation. Okay, thank you very much for this class.